know how this function looks like for arbitrary j. Okay, without proving it, I give you expression bj as a function of x. It's two Hatanges hyperbolicus, right? It's 1 plus 1 over 2j Hatangen hyperbolicus 1 plus 1 over 2j x minus 1 over 2j Hatangen hyperbolicus x over 2j. So you see, we have this function. And let's study for a while the property of this function. For two simple limits, namely j equal to 1/2, we have this tangent hyperbolicus. And those who like to do exercise can check that if we put j equal to 1/2 and we have two different cotangent hyperbolicus, it's nevertheless can be simplified in this nice and simple expression. It's a good exercise. But for spin 1 needs to massage a little bit the expression in order to get it to the form. What I would like to discuss now is semi-classical limit. I would like to plot this function and discuss several limits of it, but the first limit which I'm going to discuss with you is what happens if j is much larger than 1. Namely, if I have semi-classical limit. And my anticipation is that in this limit, the Brillouin function should be nothing but Langevin function. Let's prove. So, b, j much larger than 1 is a function of x. So, in order to do it here, I should just put j equal to infinity. So with the first term, it's cotangent x. It's simple. Here, since I have uncertainty, I have to do a little. I have to do expansion. So this is 1 over 2j, and I have to take the first term of expansion of Hatangen hyperbolicus, and this is inverse argument. So it's 2j over x. 2j cancel each other, so in fact I have Hatangen hyperbolicus x minus 1 over x, and this is L. And this is nice. Now we understand better what has been done in our semi-classical theory of magnetism, and now we justify change of summation of a discrete variable to the integration of a solid angle. So you see that this part of the theory, the semi-classical one, is already there. Now, if we have x much smaller than 1, then bj x goes to 0 for arbitrary x. What we have to do is to expand. It's 1 plus 1 over 2j, and here it's 1 over 1 plus 1 over 2j x minus 1/3 x 1 plus, sorry, x 1 plus 1 over 2j. So I will keep only first terms. It's sufficient. So this is expansion of the first cotangent. Of course, there are some other terms. For the second one, it's minus 1 over 2j, and here it's 2j over x minus, sorry, it's plus, of course. It's plus 1/3 x over 2j, plus, and so on and so forth. So the next one, for example, we know that cotangent hyperbolicus x has expansion 1 over x plus x over 3 minus x cubed over 45. Okay, let's collect terms. So this is approximately equal to here 1 over x plus 1/3 x times 1 plus 1 over 2j squared. Minus here we have 1 over x with the coefficient 1 minus 1/3 x over 1 over 2j squared. 1 over x and 1 over x cancel each other, so we have x over 3, and here we need to collect these two terms. It's 1 plus 1 over j plus 1 over 2j squared minus 1 over 2j squared. For small x, it is equal to x over 3, j plus 1 over j. This is important since we will be calculating susceptibility in a few seconds. So this is the coefficient which we have. Again, if we take j very large, much bigger than 1, then the coefficient doesn't depend on j and equal to 1/3 as it is for the large function. Let's now calculate the susceptibility. Large x behavior can be checked easily because both cotangent are confined, approaching 1 with exponential accuracy when x goes to infinity, so one can check that the function is in fact limited by 1 and minus 1. Let's calculate the susceptibility. The same definition, chi is equal to g, j, mu Bohr, n over b. Sorry, I will rather include it's equal to n over b limit mz over h when h goes to 0. But mz is given by this expression. So this is n over b, g, j, mu, Bohr, j. Now I have to replace this function by its argument. This is nothing by that, and cancel h. So this is g, j, mu, Bohr, j over 3 temperature, and here it's j plus 1 over j. Okay? So 1j is cancelled out, and what we have is n over b, g, j, mu Bohr square, j plus 1 over 3 temperature. So in fact, for quantum system, we also have susceptibility given by formula C over temperature. This is inversely proportional to the temperature. But if you look into the classical formula, you will recall that for classical definition of the Curie constant C, we had m squared there. Here, instead of m squared, which is square length of a classical vector, we have j times j plus 1, which is a true square of the quantum mechanical operator. Just observation. Okay, if we now adopt the same scheme of the molecular field, namely if we say that H effective is equal to H external plus gamma times mz. Please repeat these calculations, but what we obtain is susceptibility chi is equal to c of t minus t. So being back and plotting this brilliant function, it is very much like Langevin function. So this is E j is a function of x, and this is x. And for the case of molecular field, we arrive at equation mz is equal to g j mu or j b j g j mu or j mz as a temperature. And solving this equation, we again realize that there are two limits. If t is larger than Tc, then only trivial solution of equation exists. If, however, t is smaller than Tc, then two solutions appear corresponding to two different directions of normalization, up and down, and therefore one can again have in mind the same pictures as before, namely there is a spontaneous magnetization occurring in the system. This is mz average, and inverse susceptibility is equal to 0 at critical temperature. The question is, and this is again the problem which I suggest you to solve at home, namely, what is the behavior of magnetization in the vicinity of critical temperature? I give you a hint how to solve this problem. Namely, I would like to calculate the way the magnetization approaches 0. Let's say this is Tc minus T to the power beta. And this critical index, and hopefully from theory of phase transition, you know what critical index is, describe us the behavior of magnetization. In order to do it, what we need to do is to expand the Brillouin function up to the next term, namely cubic one, and see the definition of critical temperature. Critical temperature is defined where the slope of the Brillouin function, namely derivative, is equal to the slope of dimensionless curve here. So using this definition at Tc and allowing magnetization be non-zero in the vicinity of the phase transition point, you will find out the critical index. The critical index for susceptibility, saying that this is proportional to T minus Tc to the power gamma, and this formula is for T larger than Tc, we see here that gamma is equal to 1, but it's better to introduce dimensionless parameter. As you know, sometimes people call it tau, and this is T minus Tc over Tc. So, and I better write that this is tau to the power gamma. So gamma is equal to 1. Do you know what beta is equal to? 1 or 1/2. That's correct. That the result for beta is equal to 1/2, and you will see that the same law actually occurring in all mean field theories describing second order phase transition. So what we see here, again physically, means that below Tc we have spontaneous symmetry breaking, and spontaneous magnetization. So at very low temperatures, system wants to be aligned along z direction, and all spin wants to look in one direction. Above critical temperature, we have disordered phase with a higher symmetry, where the average magnetization, the uniform magnetization, is equal to 0, and magnetization appearing just in response on a magnetic field, like in the ferromagnet which we discussed before. The magnetization is proportional to applied. While here it is spontaneously broken. Sometimes people discuss that kind of phase transition in terms of Landau theory, which says that if we plot, say, free energy as a function of temperature, then for temperature larger than Tc, there is only one minimum, while for temperatures larger than Tc, there are two minima. So a system decides to which one to go. So these are precisely these two minima corresponding to two different directions of magnetization, because when you don't apply magnetic field to the system, both direction along z, parallel to z, and anti-parallel to z are equivalent. Are you familiar with Landau theory of phase transition? I'm not going to go to detail because Professor Yevtushenko will anyway tell you about both Landau theory and Ginzburg-Landau theory of the phase transition. But what one has to know that we are doing precisely this sort of things. Okay. Any questions regarding that? Because in the remaining 10 minutes, I will start writing microscopic theory and introduce a Hamiltonian. And next week we will work with this Hamiltonian, write down version of mean field theory for this Hamiltonian, and find the susceptibility as a response to space non-uniform magnetic field. Therefore, we find the susceptibility as a function of Q, as a function of the wave vector, and we see what happens in the susceptibility when we take limit of uniform magnetization, namely Q goes to 0. Yes. And also see what happens with the theory when the parameter tau approaches to 0, namely what happens in the vicinity of phase transition if we are approaching to the phase transition from disordered phase. But now, since I know that we discussed some Hamiltonians, let me start with the simplest one, simplest in quotations. Let's now define microscopically how spin talk to each other. And I will write the Hamiltonian in such a way that this is G M M S M dot S. And this is a Heisenberg Hamiltonian. Well, there are many arguments to convince ourselves that this is the simplest one. One can derive this Hamiltonian for starting with Slater determinants non-interacting system and introduce some Coulomb interaction and taking matrix element of a Coulomb interaction and then using the symmetry. But one can also say that, look, if we have spins and if we assume that only pairwise interaction occurs in the system, so namely only neighbors talk, and only such neighbors the pair of spins interact. Of course, in a lattice, suppose I have square lattice, it means that this spin talks to this one, it also talks to this one, it also talks to this one and to this one. But they're talking pairwise. Namely, it's not the situation where these three spins talk together, because this is more complex form of the Hamiltonian, and we would like to start with the simplest one. So the idea of simplicity is quite reasonable one. So let's postulate that this Hamiltonian takes place, and of course, if we confine ourselves first the assumption that only pairs of spin talk, and we want to have a simplest form constructed from spin operator, then the simplest Hamiltonian will just contain a scalar product. Because we need to construct a scalar, the mean value of the Hamiltonian, which is energy, is a scalar. Therefore, the simplest form is a scalar for the Hamiltonian. I know that in the course of advanced statistical physics, in the course of Alessandro Silva, you discussed Isaac model, which is particularly a realization of Heisenberg model of anisotropic one. Let's formulate anisotropic version of the Hamiltonian. It's minus J n m x s n x s n x plus G n m y s n y s n y plus G n m z s n z s n. So this would be anisotropic realization, still scalar one. The Hamiltonian is scalar, where the fact that spins talk differently along x, y, and z direction. And from this Hamiltonian, we can easily arrive to the situation, for example, where x and y are equal to 0. This is Isaac model. Or if z is equal to 0, but x and y are equal to each other, then we have xy model. And this is what I think we discussed. I will generalize this notation. I will define the situation that if J and M z direction is much larger than G and M x and G and M y, then we can speak about easy axis magnet. Because z axis of magnetization is so-called easy axis. It's a preferable direction of magnetization, like an Isaac model. Although two other components still talk to each other. So this is easy axis model. And again, in literature, you will meet this terminology quite widely used. On the other hand, if we have oppositely G, X, and M, G, Y, and M are much larger compared to G, N, and Z, then we have easy plane. Easy plane means that spins are preferably aligned in the plane, and Z interaction is weak compared to XY. So you see that this Hamiltonian is quantum, namely free projection of spin operator do not commute with each other, as we discussed it today, one cannot measure all three components simultaneously, and due to this non-commutativity, many interesting phenomena occur. So, the program for next lecture. I will probably stop today because I need to start some involved calculations, and I would prefer to start it next time. Otherwise, I will need to repeat most of them next time. Anyway, let me formulate a program. What shall we do in the next lectures? In the next two lectures. First of all, I will assume that temperature is larger than critical temperature. Make a Fourier transform of the isotropic Heisenberg Hamiltonian and calculate the susceptibility of the system as a response to magnetic field, which is Ez times H times cosine you know R. So I will introduce some non-uniform magnetic field with changes in space and calculate the response function on this field. This will be done using molecular field theory applied to this Hamiltonian. Then what I will get is the susceptibility. I'm still discussing static effects, so nothing depends on time. Depending on Q mode, will behave as C over Tc, and here temperature minus Tc over Tc plus Q node A square over C, where A is a lattice constant. So you see that if we denote this as tau, then this is C over Tc, and here 1 over tau plus 1/3 and this expression is known as Einstein-Theoretic formula, and actually plays a very important role in the theory of isolation. So we derive it microscopically for specific model of Heisenberg interaction between nearest neighbors, and we discuss what happens, what is the correlation length, what is the meaning of correlation length, and what is happening in the system when we approach to the critical temperature from the disordered space. It will be subject of one lecture. I would like to discuss it in very details. The subject of a second lecture would be to consider the same Hamiltonian but use another limit, namely if we are sitting here. If we are at temperatures much smaller compared to critical temperature, and moreover, if we are in almost ordered state. We will calculate the excitations in this system and find out what is the dispersion and what the thermodynamics associated with this excitation, and what is behavior of magnetization. And excitations will define as behavior of magnetization in the vicinity of magnetized state. This will be enough. And let me call it magnetism. And I spent yet another lecture devoted to local magnetism to discuss different situations. Namely, what happens if we have several sublattices. For example, if you look at this Hamiltonian and ask me why did I put sign minus, and this is convention actually, which assumes that all J and M are positive, and if it is so, then the ferromagnetically ordered state is most favorable one. So for the Hamiltonian defined with exchange integrals all positive, the state where all spins aligned in one direction at zero temperature is a ground state of the system. An excitation described as what happens above the ground state. However, if for the moment I assume that exchange integrals are negative, and I said that this is some matrix elements which can be negative or positive depending on the wave functions which we use to calculate this matrix element, then if we assume for the moment that J and M for nearest neighbors, let me put it this way, are negative, and J of course depend on difference Rn minus Rm, so more we deviate from nearest members, the smaller interaction is, then we are in a delicate situation that spins want to be oriented anti-parallel because this minimizes energy, and we arrive at anti-ferromagnetic states. So we discussed in one lecture anti-ferromagnetics, what is correlation function at temperature above critical one, and what is the excitation spectrum in anti-ferromagnetics, where having two opposite directions of spin, we need to define two sublattices. And then we come to discussion of correlated systems, which will be built. So this is program for theory of magnetism, but meantime I think I need to arrange one tutorial about semi-classics because this is crucially important for your education. Questions? If not, let's see. So we discussed with you. So let me finish magnetism and we start to think what could be interesting program. No, it's other way around. To have a superfluid, we need to first have a condensate, this coherent state described by a single wave function. And as soon as we have a condensate and interaction, then we can manipulate its phase. And actually, what is done, if we create a gradient of phase, then we have a current. And this current will flow without any energy loss. So condensate actually provides this possibility to have superfluidity. So to say, one cannot have superfluidity without condensate, but one can have a condensate without superfluidity. So condensate provides us the modulus of the wave function. and possibility to describe many body quantum state with a single wave function, like a single particle, global wave function for whole system. But phase of this system provides us possibility to make a superfluid, because we can create a gradient of this phase in a current lines. The same way they destroy superfluidity.
Yes. And in New York, for example, you have iteration is strong, you have strong iteration.
Yes. Yes. This is why, I mean, the theory which I described to you was a theory of weakly interacting system. Helium appears not to be weakly interacting system. The interaction is strong. Therefore, there should be some other theory, because as I said, the fraction of condensate is about 8%. So helium is a bad example. But there are some good examples for this theory. For example, this alkali metals, gases, is very well described by the weakly interacting theory. But you're right. The effect of interaction are very crucial, and interaction suppress the condensation. But then one needs to have reliable theory, to have a small parameter. And for the theory I try to explain you, the small parameter was the smallest. This is always a problem with strongly correlated systems. What is a small parameter? If all correlations are strong and the system is not dual, you know, sometimes when there is a dualism of the model, one can construct some information theory with respect of the growth.